Hello, everyone. Let's start today's discussion. Today, we are going to talk about the IEEE 1547, which is the standard for interconnection and interoperability of the distributed energy resources, which we call it DER, uh, with the electrical power system interfaces. Now, this standard is the foundational to modern electric grid integration. So it sets some technical and operational and also communication requirement for those DERs so we could make sure that we have a safe, reliable, and flexible power system. Okay. This discussion today, we are going to talk about the definitions. We are going to talk about first, we are going to talk about the standard itself, why we developed that, what is the scope and purpose of this standard, and then we go through some definition and protocols and requirements defined by this standard. We are not going to go through the exact approaches that you can have to apply those requirements. It is going to be beyond the time and the scope of this discussion, but I really encourage you to go through the standards. It is very helpful for you to understand the aspects of power grid and the integration of the distributed energy resources and the metrics that are important for us when we talk about the grid integration. Now, let's start with the fundamental question, why we actually have this standard IEEE 1547. What are the key drivers for IEEE 1547 adoption? Now, first of all, this standard is not a solo, is not emerged in an isolation. Okay, there are some complementary standard. We are going to talk about a bunch of them. That this standard mandates following those standards too. This standard was a response to some critical technological and operational challenges that were introduced by modern distribution energy resources. And one key reason for developing this standard is proliferation of inverter-based resources. Okay. Now, there are, as you know, a rapid increase in a roof-bar solar PV and generally the solar photovoltaic generation, the battery energy storage system, and the electrical vehicle supply equipment, which basically fundamentally changing how electricity is generated and consumed and at the distribution level, which unlike the synchronous generator and the traditional system, all these technologies are inverter-based resources, and they rely on power electronics to interface with the grid. So the inverter are the main component in those systems. Okay, now the traditional, why this is important? The traditional grid uh, basically were developed for large rotary machines. Okay, with inherent inertia and stable frequency voltage responses. But the inverter-based resources, because they are in a power electronic and they use switching devices, they respond much faster. And basically, if they are not coordinated, they can behave unpredictably. So they can cause some voltage flicker or harmonic distortion or reverse power flow, which are very important challenges when we talk about the modern power grid. Now, because of those challenges, we need to have a standard like write-through or reactive power support or harmonic limitation. So we could make sure that those devices basically coexist safely with our grid. So this standard, basically the IEEE 1547, provides some mandatory, also provides some mandatory communication and control requirement. Okay, so utilities can manage the distributed inverters as part of their grid. Now, we said we are going through a shift to the modern power grid. So there is a transition to different topology, different nature for our power system. Now, this is a transition to the distributed generator. The power grid basically is shifting from the centralized generation model, which was the large power plant transmitting electricity in one way, one direction, to distributed generation, the DG models, where we have many small resources that generate electricity and they are closer to the loads. Okay, so those DGs, this is one of the major challenges. Those DGs, those distributed generators, introduce a bi-directional power flow. This is one of the main differences between the traditional centralized model and the distributed model for the power system. So before we have a unidirectional flow. Now we have a bi-directional flow. Okay, which basically when we talk about the system, the legacy and the traditional protection equipment or voltage regulation system, they are designed based on the unidirectional flow, based on the traditional system. And without having a standard requirement for the distributed resources, the feeder can have overvoltage, which happens when we say that reverse the bidirectional, which happen when we have excess of DER output, which means we are pushing a reverse power flow from the downstream distribution system to the upstream feeders in the distributed system. So that reverse power flow could create some overvoltages in the upstream feeders. Now, beside that, we have some islanding risk, which is basically create a lot of like safety problem in the grid. We are going to have some coordination issues, which rises when the thousands of small DERs operate independently. Now, IEEE 1547 defines some interconnection rules or trip or reconnection criteria or anti-islanding protection. So we could make sure that those DER behave predictably. Okay, so by mandating the parallel operation guidelines, we make sure that those DER are synchronized with the grid for both like voltage and frequency before they are integrated to the grid or reconnected to the grid. Okay, so another aspect that was basically one of the reasons of developing this standard was grid instability concern, which is a critical, basically a make or break kind of like situation, the instability of the grid. Now, when we're talking about increase in a penetration of variable renewable resources like solar or wind, this basically introduced a volatility in a power supply, meaning we have frequency instability or voltage sags and swell or power quality disturbances. Now, let's step back and talk about this. When we talk about a variable, for example, a PV system, you can have, it doesn't matter how much you have like how much advanced your control system and your technologies, you can't basically have a constant controllable power generation because like in solar, you are transferring sun light energy, solar energy into electricity. So if you have a cloudy day or during the different hours during the day, you will see a certain level of variability in the power generation. Same goes for like wind or some of the other DERs or renewable energy resources that are connected to the system as distributed energy resources. So these unpredictable, out of control variation can provide some challenges. Now, without having any standard requirements, basically to meet those challenges, every DER manufacturer uses different settings. And if we have different settings and a vendor-based kind of like configuration, now we have an uncoordinated responses when we are dealing with those fluctuation or any disturbance in our system. Okay. Now, the IEEE 1547 introduces some like right-through requirement. Okay, like voltage right-through and frequency right-through. We are going to go deeper into those protocols. Or in the standard, some reactive power control. So it could help the DER to actively support the grid's voltage stability. Now, because of those reasons, this standard was developed. So the first purpose of this standard was to have a safe integration. Okay, what that means? The objective is to make sure that the DERs can interconnect without the compromising the safety or reliability of the utility personnel or customer or equipment. Okay, so the key aspects are like defining a uniform technical specifications. So all the DERs, regardless of their manufacturing system or the manufacturer, follow the same electrical interconnection rules. This also includes some strict anti-islanding requirements. Okay, so we could protect the line workers during the outages. So DER must disconnect quickly if a portion of the grid become de-energized. So if they don't do that and they switch to islanding mode, then it would violate the de-energization of the part of the grid that are under maintenance, and you can see how dangerous it would be for the workers that are maintaining those and working on those equipment and our system. Now, this standard also establishes, to meet the safe integration, establishes the trip and reconnection rules. So we prevent some unsafe energization of the grid. Now, we have an aspect of the interoperability in our purposes, within our purposes of this IEEE 1547, which basically makes sure that the DER are not just connected, they can also be coordinated with the grid. Okay, so it mandates some communication and control capabilities. So that basically utilities and utility owners can remotely monitor, control, or even adjust the DER parameters. It could be like a power factor or active reactive power, or those right-through settings that we are going to discuss. Beside that, it enables the DERs to have an event-based dispatch capability. Okay, so utility can ramp down the DER output during the emergencies or schedule a certain setting for the peak demand. Okay, now another purpose is the protection guidelines. So we wanted to like protect both grid equipment and the DERs when we talk about the abnormal system conditions. So by specifying some monitoring and testing or like commissioning procedure before the DER is activated, we make sure that we are protecting both grid and DER. They are also required to meet some harmonic limits, harmonic distortion limits, or maintain the power factor within a certain specified limits. or follow some voltage regulation rules. These are all for protecting the grid and customers and the DER itself, which it's also include those right-through requirements that we are going to talk about. Now, these are the purpose, but what are the scope and limitation of a scope for this standard? As you know, every standard has its scope, so it applies to a certain categories of equipment or systems. It's not a general kind of like rules for everything. Okay. Now, what are the system? First aspect that limits the scope of IEEE 1547 is that this IEEE 1547 applies exclusively to interconnection at the distribution level. So when we talk about a transmission level system or like a bulk power grid, this standard do not cover those levels. Okay. So another aspect is that it's limited by aspect of parallel operation. What that means? It means it applies to the DERs that operating in parallel with the grid. Okay, so if we have any resources, okay, that works standalone, like in emergency backup generators, they are not covered by this standard. Okay. There is also a capacity range. Okay, this scope of the scope of this standard actually covers a very wide range of capacity from like kilowatt to megawatt capacity of the DER, but it is limited to the capacities of the distribution level system. Okay, so it's important to notice the limitation in the scope of this standard. So we make sure that we know where to apply this requirement and where we should not apply this requirement. Now, we said we are going to talk about, and that's actually the objective of this standard is to talk about and address the issues that were introduced when we shifted from the traditional power system to a modern power system. But what is the importance of this standard in a grid modernization? Now, we said the power system basically evolved and DERs become a dominant part of the electricity generation. So now the standard that basically defines the criteria and requirement for DERs become a critical component when we talk about enabling this transition and addressing those technical challenges that are caused by the integration of DERs. Now, one aspect is addressing the reverse power flow. We said one of the big differences between the DER and the centralized model that we had in traditional system is that in a modern system, we have reverse power flow. We have bidirectional power flow. Now, we said that the traditional grid flow is basically unidirectional. So from the centralized power plant through the transmission line and the distribution network, all the way to the consumers, we have a one direction. Power flows in one direction. But when we have a high DER penetration, it could be PVs, it could be batteries or electrical vehicles, power now can flow backward. So we could have a reverse power flow. When that happens, when those DERs, which are closer to the load, which are in a downstream of our system, produce more power than the demands in their local system. Now we have an excess of the power generation, which that one would flow back to the upstream feeders. causing some overvoltages. Uh, and this also, as we mentioned, it could confuse the protection system, which the traditional one are designed for a unidirectional flow. Beside those is also can, if they are not properly managed, the transformer could be overloaded. Now, IEEE 1547 defines some specific modes, control modes basically, to address that. So we have volt watt mode or volt var mode. Okay. When we try to mitigate by controlling the active and reactive power, we try to mitigate the overvoltage. Basically, those DERs automatically reduce the real power output as the voltage rises because of that reverse power flow. Or they provide some reactive power absorption to control the voltage. Okay. Now, another aspect that makes this standard very important in a modern grid is the mitigation of the frequency instability. As we mentioned earlier, traditional grid were basically rely on rotary machines, like synchronous generator. Those rotary machine has like natural mechanical inertia and an stabilized frequency. But the DER, and particularly the inverter-based one, they have basically little to no physical inertia. And when we have a high penetration of those DER, basically means that our grid is more susceptible to frequency fluctuation. Okay, so a rapid frequency change during like a sudden load or any fault uh, could be seen when we have like a high DER penetration, or we could have like a cascading DER tree. If they disconnect to the too quickly, when there is a frequency drift outside of their acceptable limit. Now, what IEEE 1547 do for us in this aspect is to introduce the frequency right through, or introducing some specific frequency droop control. So we could control and actually help the DER could help the grid and the distribution system to stabilize the frequency if there is any deviation. Now, another aspect is reducing the power quality disturbances when we talk about the grid in the modern grid. Now, we said the inverter-based resources normally use a power electronic and switching devices, which work in a high-frequency switching situation. And as you can imagine, that could introduce some harmonic or flicker or voltage fluctuation into the grid. So that makes power quality to have a very poor power quality, which could damage the sensitive equipment or interfere with the grid protection or communication system, and reduce the overall efficiency of our power system. Now, this standard comes in and mandates the compliances with harmonic limits defined in the complementary standard IEEE 519. It also requires the DERs to maintain the voltage flicker within a certain permissible limits, and also make a rule that says that the DER should operate in a certain range for the power factor. That way, we can make sure we have a level of power quality that cannot and will not jeopardize our grid stability. It also, the standard also covers some requirement for testing and monitoring protocol. So we make sure now with that we have those requirements and those quantitative limits, how we can monitor them and how we can test that, okay, RDR doing a proper job meeting those requirements. Now, last aspect is that when we talk about distributed resources, we are going to talk about like thousands of small resources that are everywhere in our grid, and the utility owners and the control system should deal with all of them and coordinate all of them. So that means we need a proper communication system. So we could actually control, manage, and coordinate those distributed resources. We have to have a remote access to adjust the DER settings, or basically utilities could be able to make sure that they respond effectively when there is a grid emergency, or coordinate those DER dispatch for like demand responses. Okay, now to meet that, this standard IEEE 1547 defines some interoperability and communication requirement. There are some complementary standards like IEEE 2030 Part 5 or IEC 61850, which helps to meet those communication requirements. Okay, there should be a secure remote configuration and monitoring system and firmware update. And those communication system should, and the interoperability system should support the event-based dispatch. So they could allow utility to actively manage the DERs when they have like a peak demand or any kind of emergency. Now, we talked about the purposes. We talked about the general requirement that these standards addresses defines to address the challenges in a modern grid. Okay, but we know we can't define the requirement or any quantitative criteria or metric without defining where to apply those, where we should monitor those, what those requirements apply to, and where apply to. Now, these standards define some important key interface points for our procedure and protocols for grid integration of the DERs. The first one is the electric power system, area electric power system, or as we call it, area EPS. The area EPS refers to the utilities distribution network. Okay, so when the distributed energy resources are interconnected. So it includes all the utility control lines or transformer or distributed equipment upstream of the customer. Now, remember, this is the utility part. Area EPS is the utility part. Next interface is the local electric power system, which is a local EPS. Now, the local EPS is the customer side of electrical system. It could be an on-site DER or a local load or internal wiring or breakers, and basically customer-owned equipment and transformers or stuff. So the local EPS is the customer side. Area EPS is the utility side. Local EPS is the customer side. Now, area EPS is the target of this standard. What I mean by that, we define all those requirements and all those protocols because we want to have a stable situation and meet and address some challenges. Okay, those problem and challenges are the area EPS challenges. So all the standard requirements are defined so we could make sure that area EPS is stable and works in a proper condition. So each requirement, when we wanted to like control if we're meeting the requirement, we actually measure the impact of those aspects on area EPS. If the impact is within the acceptable limit, we're meeting the requirement, we are good to go. If we're violating those limits, we need to kind of like adjust certain metrics to address that problem. Now, local EPS is the part that actually have a potential of creating those problems. So if we talk about the harmonic distortion and we want to control it, is basically local EPS that creates those harmonic distortion, and we need to control it. So we make sure the area EPS is not affected by harmonic distortion or any type of like challenges. Now, we have two parts, area EPS, local EPS. The point that they meet, we call it point of common coupling. So you can imagine when we talk about the effect of local EPS and their impact on area EPS, and we want to like control, monitor, control, and address and apply the requirement, address the challenge and apply the requirement. Okay, all of those happen at the point of connection between these two. So on the point of common coupling. So basically, the PCC, the point of common coupling, is the most downstream point on the area EPS, which is when the customer system meets the utility system. Now, every measurement that we conduct, any test that we conduct, or any command that we apply to our system would happen at a PCC. This is the point. This is the reference point for our work. Now, we define the interface point, and we talked about the general purpose of the standard, but we mentioned DERs a lot in our discussion so far. But DER are not, all of them are not just the same configuration. This standard actually categorize them into two different class. So we have two different class or two different category for the DER. Okay, so the requirements are different for those classes. We have one class named controllable DER. Those controllable DER are the one that can be actively managed or commanded by the local controller or utility signals. Okay, so it could be like a smart inverters or battery energy storage systems or microturbines with a remote dispatch capabilities. So basically, those controllable DERs should support the advanced functions defined in the IEEE 1547, like that volt var that we mentioned, or volt watt that we mentioned, or frequency group control. So these controllable DERs are the one that we can use as a tool, as a leverage to address the challenges and apply those requirements at the point of common coupling. Now, the other class is non-controllable DERs. From the name, you can expect that these are the DERs that cannot adjust output in response to any external commands. So they operate independently, and they operate based on the environmental local condition and their internal actually settings. So it could be like a basic rooftop solar, okay, or in a small wind turbines with a fixed speed induction generator. Now, Because those non-controllable DER have a limited interconnection functionality, okay, they only need to meet basic requirement like anti-islanding or trip reconnect requirement. Okay, so or the harmonic kind of like distortion requirement because they cannot participate in active grid support functions. Now, we mentioned the classification of the DER. Let's talk about the metric that we could actually monitor the situation in the grid and how good we can like address those problems that exist in the grid. One of the aspects that we could define the metric based on that is the power. As you know, we have different metric when we talk about the power itself. One is active power. Okay, the active power, the definition is the actual work, the amount of power that do the actual work for us. The unit is watt. Okay, and basically it represents the energy conversion into a useful form. Okay, now IEEE 1547 defines the real power control functions. So it could apply those requirements to address those challenges that we mentioned. So we could have like a ramp rate limits that controls how fast the DER output can change. Or we could have like a maximum power limit. By power, I mean active power, which caps basically the DER output so we could avoid that reverse flow and feeder overvoltage. Or we can have like a volt watt mode, okay, which it reduces the output active power automatically, okay, when the generation demand is unbalanced and the generation is more than the demand. So again, we could avoid the feeder voltage rises and that reverse power flow. Now, another metric is the reactive power. This part do not do any real work for us, but it is required to maintain the electric and magnetic field in our system. The unit is VAR, VAR, which is short for volt ampere reactive. Okay, and basically is power stored and released by the inductive or capacitive elements in our system. Now, IEEE 1547 use this metric for a certain kind of like regulation, voltage regulation, and power quality regulation. One would be like volt VAR mode, when basically the DERs are asked to dynamically adjust their reactive power based on their measured local voltage so they could help stabilizing the voltage of their feeder. Okay, we could have watt VAR mode. Okay, so they could adjust the reactive power based on the active power output. Or we would use this reactive power when we talk about the constant reactive power mode as one of the protocols defined by IEEE 1547, which allows basically a fixed reactive power injection or absorption to compensate the system's need for active or reactive power. It mostly happens when we have like a load, a consistent load pattern. So we know how much active power, reactive power, how much reactive power we normally need. So we set it in a constant reactive power mode. Now, when we have active power and reactive power, now we can define apparent power, which is the vector sum of those active and reactive power. You can imagine, you can see the in the slide in the image that how those active, reactive, and apparent power relate to each other. Okay, and basically the magnitude of the apparent power is the square root of active power square plus reactive power square. This apparent power is used in IEEE 1547 for DER sizing and the power factor verifications. We're going to talk about that. A power factor, as you can see in the slide, is a ratio of real power to apparent power. So if we know the apparent power and we know the active power, now we can control the power factor. Now we can measure the power factor. We can adjust the power factor. So it also can be used sometimes for the reactive power control, because sometimes instead of like directly defining the war amplitude, the reactive power amplitude, we define the reactive power as a percentage of the apparent power. Okay, like for example, like we could have like a 100 kilovolt ampere inverter, which provides 80 kilowatt real power. Okay, but it still needs to supply like a 44 plus minus 44 kilowatt reactive power, which means when we want to like define that, we say, okay, that inverter needs to provide 44% of rated apparent power based on IEEE 1547. Now, as we mentioned briefly, we have also a metric of power factor, which is the ratio of the active power to the apparent power. And basically it indicates how effectively electrical power is being converted. Why is that? The S, the apparent power, is the whole energy, is the whole power that a DER injects into the system. Now, we said the active power is the portion of the power that actually do something for us. So the ratio of that is basically indicates that how effective our electrical power is. What portion of the entire power that he injected actually do something. And its power factor is equal to P over S, which is equal to the cosine of the theta that you can see between the S and P. Now, it could vary between 0 to 1. The power factor range is 0 to 1. 1 means we have purely active power, and 0 means we have purely reactive power. 1 and 0 would not happen in real world, okay? But they are the ideal top boundary and low boundary of the power factor. Now, IEEE 1547 defines a certain limit that the system, the DERs, should work regarding the power factor. Like for example, it's like 0.9. They should not let the power factor go lower than 0.9. It could be lagging or leading, okay, regarding the reactive power portion, okay, but the power factor should remain higher than 0.9 based on this standard, IEEE 1547. Now, we said one of the most important requirement that addresses some stability challenges in our modern grid is the right-through behavior and right-through requirement. Okay, so let's talk about the permissive operation and what we mean first before we go to the right-through. Now, the IEEE 1547 basically says that we have to have a permissive operation, meaning a DER is allowed and often expected to remain connected under a certain abnormal condition. Okay, so what is the purpose for this? It's preventing the system-wide cascading tripping. Or and most importantly, it actually provides active voltage and frequency support for the grid by staying online. The DER stay online and provide that support. In the old approach, those DER immediately trip when they see any deviation in a voltage or frequency. But now they have to stay connected and follow the right through requirements. Now, we said already that we have two types of right through. One is the frequency right through, which is the ability of the DERs to remain connected uh, and operate during the temporary deviation of the frequency. Okay, now we have a certain interval defined, like it calls the standard calls the right through zone, frequency right through zone, that defines the response of the DERs to a certain deviation, to a certain amount of deviation in the frequency. For example, one of the interval is if we have a frequency deviation that happens between, for a 60 hertz system, okay? We have a 60 hertz system. If the frequency deviation is between 59.3 all the way to 60.5 hertz, okay, if we are within this interval, DERs are not allowed to disconnect. They should maintain their operation without any disturbance. Now, if this lower border, the under frequency, happen to go between 57 hertz all the way to that 59.3, now the requirement is different, but the IEEE 1547 requires those to stay connected for at least 300 seconds. After that, they could seize the energy or trip in this area. Now, if over frequency exceeds that 60.5 and goes from 60.5 all the way to 62 hertz, okay, again, the DER should stay connected 300 seconds, and after that, they could trip. Okay, now we also, as we mentioned, have another right through requirement, which is voltage right through. Okay, which basically is the ability of the DER to remain online during a temporary voltage sag or voltage swell. Now, again, IEEE defines some interval and zones, and based on those zones, how much deviation we have in our voltage, we define how the DER should react to those deviations. Now, the first zone is when we have a deviation that is between 0.88 to 1.1 per unit of the nominal voltage. These are per unit, okay, of the nominal voltage. If the deviation is within that interval, they are not allowed to seize or trip. So they have to stay in a continuous operation mode. Now, we don't allow the system to go higher than 1.1. So if something happened, the system would trip, the relays would activate. Okay, so but the lower bound could go lower. So if we have a more under voltage deviation, which means between 88, the next interval, and 0.7, okay, this is the interval. If we have this interval, of per unit voltage. Now they are required to stay connected for 10 to 20 seconds, okay, and then they could disconnect or seize the power. Now, if we go further and it happened to have like the deviation is 0.5 to 0.7, now they are allowed, they are required to stay connected for 0.60 second, which is basically 160 milliseconds, which for a 60 hertz is 10 cycles of our sinusoidal function. Okay, and after that they could trip. And if we go below the 50, the 0.5, then they could immediately trip. And we don't have any problem. Now, it's another aspect of the write-through is the seize of energy. Let's say we go beyond those interval for write-through, for both frequency and voltage write-through. Now what's happened? It's not that they instantly could trip. Okay, there is another requirement, meaning which we call it seize of energy. Okay, uh, let's first define what is the difference between seize of energy and trip. When we talk about the seize of energy, okay, it means to stop injection of the current, but we electrically is still connected to the grid. When we talk about the trip, trip means fully disconnected, like fully physically disconnected from the grid. In seize, we are connected to the grid, we just don't inject current. In trip, we are disconnected from the grid. Now, all the DERs are required to seize the energy before the trip. To seize the energy, okay, within the 2 seconds, for at least for 2 seconds after they detecting the deviation outside of those write-through interval, or an unintentional islanding would happen, or a fault detection or a utility trip command is applied to those DERs. So even when there is a situation that they are allowed to disconnect, first they have to seize the energy for 2 seconds. If we have a still the deviation and is not cleared, now they can trip. But when we talk about the tripping or the seize of energy, it means, okay, we seize the energy or tripped. Now the system is go back to the normal situation. We have to reconnect, okay, and start injecting power again. But we can't do that haphazardly. There are rules for that too, okay? So the IEEE 1547 says that the DERs can reconnect only after the voltage and frequency return to the normal, okay, operation for at least 5 minutes. It's not just instantly after they get to the normal. Okay, so if the grid can maintain the normal voltage and frequency for at least 5 minutes, now they can go back. Plus, there's another condition. They should confirm that they are synchronized with the grid before they reconnect. So we have 5 minutes that the grid is healthy, the voltage and frequency is stable, and our DERs can confirm that they are synchronized with the grid, which means the frequency, phase, and voltage is synchronized with the grid that they want to connect to. Then they are allowed to start reconnection, but it's not an immediate action. They cannot go full power immediately. There is another requirement which requires the DER to have a ramp rate limit for increasing the power after they started the reconnection until they get to the full load of the power. And normally it's 1%, 1% per 1 second. So it's a linear ramp which allows them to increase the power after they are allowed to reconnect. Now you can adjust, this is a default, we can adjust this 1%, but the range should be between 0.5% all the way to 10%. You can go faster than 10% per second. And you cannot go slower than 0.5% per second. For 0.5% per second. Yes. Okay. We also mentioned earlier that beside all those electrical requirement, the power requirement, because we have a geographically wide grid and we have thousands of DERs distributed on that massive grid, for having real-time monitoring and control over those resources, we need a interoperability and communication system. And when we need a system, we need to make sure that they are a standard, so we know we have a common rule for everything. Now, when we talk about the communication interface, it's basically the physical and logical link between the DER and the utility grid or the grid management system, which basically enables the data exchange or remote control or firmware updates. Okay. Now, the requirement for these communication interface that are defined in IEEE 1547, okay, is that they have to follow some mandatory standard protocol. Okay. One standard is IEEE 2030.5, which we call it a smart energy profile. Another standard that is required by IEEE 1547 is called SunSpec Modbus, okay, which is a lightweight and widely used protocol for local monitoring and configuration. Okay, normally, like inverter manufacturers use that. It's very common in inverter manufacturers. Or another required standard and protocol is DNP3 or IEC 61, excuse me, 850, which is normally preferred for utility SCADA integration. Now, it's not just that. These are the technical requirements. We have another requirement for the communication interface, which is the cybersecurity requirement. So we have to make sure that the communications are encrypted and are secure. And the DER also must allow the local configuration and like a remote access through that communication interface. Now, we talk about the controlling. So if the ability of the DER to exchange information and respond to the commands in a kind of like a consistent standard way is called interoperability. Now, we have some functions defined for that in IEEE 1547. So basically, DERs should accept remote commands. It could be like active power limits or reactive power settings or trip and seize commands. Okay, so they also should report their status and some monitoring criteria. Like we said, we are gonna have like a voltage, frequency, active power, reactive power, apparent power, power factor, all of them, which are measured at point of common coupling at the PCC. All the DERs should report that to the control center, plus their operational state, plus their ride-through events. So if anything happen, or like a trip happen, or a protection operates, anything that's happening in a DER site, they should send those information to the control system and be able to accept the command from the control system. Now, they also should have like a scheduling and availability uh, capability, which is basically support for time-based or event-based dispatches. Okay. Another option that we also mentioned briefly is the firmware updates. Okay, so DER should be capable of a remote firmware update. So if the grid requirements evolve, we could apply the new settings and we make sure that long-term compliances with the standard. Now, let's go through the general requirement for interconnection. We mentioned some of them. We wanted to like repeat those to make sure we are good to go. Okay, we know everything. One is the parallel operation. We said the DER should operate in parallel with the utility grid under the normal condition. Another one is the voltage regulation. So they should maintain a stable voltage level. There is a specified range, okay, and they should remain in that range. We have a voltage fluctuation aspect, which the DER basically have to minimize the voltage flicker and operate without causing power quality issues. Another aspect was harmonic control. We said that they have to maintain their harmonic distortion within the limit, and we said those limits are specified in IEEE 519. We also mentioned another aspect, another requirement is power factor. Okay, so they have to have and operate within a specified range for power factor. We said it's typically 0.9. It could be lagging or leading, doesn't matter, but it should not go lower than 0.9. Now, another aspect that we mentioned is the voltage regulation capability. Okay, we talked about that. We could have several protocols to help the voltage stability and regulation of the local voltage at the PCC. One would be the constant power factor mode, okay, which basically maintains the ratio between the real and reactive power. Okay, and basically IEEE specifies that DER should be capable of operating continuously within those range of a power factor that we define, which is this mode is primarily used when the utility wants a static voltage support and minimal real-time variability. Another capability is the volt-var mode, which is a dynamic reactive power control. Okay, and this is the primary dynamic voltage regulation, okay, which is mandated by IEEE 1547. In this mode, actually, the DER adjusts its reactive power output, and it continuously as the function of the measured voltage at the PCC. Okay, so it could stabilize the power. So when the PCC voltage drops below nominal, we have under voltage, the DER basically inject lagging reactive power, which is a positive reactive power, to support the voltage recovery. And if we have over voltage at the PCC, basically that DER absorbs leading reactive power, which is a negative reactive power. which mitigates that overvoltage uh, 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 and help the stability of system. Now, another capability of the voltage regulation is volt-watt mode, which is a real power requirement for overvoltage mitigation. We already said that there is a reverse flowback. So if the demand uh, fall below the generation, we will have reverse power flow, which can cause overvoltage in upstream feeders. By having the volt-watt mode, we make sure that that doesn't happen, and we could address those overvoltages and keep them in a specified range. Next one is the constant reactive power, okay, which we mentioned, which is normally for industries or commercial feeders with a consistent load profiles when we have a constant reactive power, which allows the DR to maintain a fixed reactive power output independent of the voltage or real power generation level. Okay. Uh, so these are the capabilities that are mandated by IEEE 1547 to address the voltage regulation problem. Now, to sum up the another important aspect of the requirement applied and defined by the IEEE 1547, we talked about the C's to energy, to energize, or C's of the power, which we said if the abnormal conditions fall beyond the right-through boundaries, the DER should seize the power, seize the energy before they are allowed to trip. So if the voltage get outside of the right-through limits, or frequency goes outside of the right-through limits, or there is a fault detection at the feeder, or an unintentional islanding, or there is a direct utility command, they need to seize the power. And we already talked about the requirements, so they have to at least seize that for the 2 seconds after detecting those abnormal situation, okay? And then they are allowed to move forward for tripping. Now, for the tripping, which is the physical disconnection from the power system, they should happen after the cease to energize, after that 2 seconds, under a certain fault or abnormal condition or safety issues. So we said, like, there is a voltage or frequency fluctuation outside of the right-through, or a utility command the trip, okay, or the equipment protection function find out that, okay, there is an abnormal situation or a fault that could endanger the equipment itself. So tripping the DER is better than losing the DER. Okay, so these are the conditions that they are allowed, the DERs are allowed to trip. And we also mentioned, okay, we have a trip. After clearing the abnormal condition, now we have to come back, but is not haphazardly. So first of all, we need to make sure that the voltage and frequency of the grid return to the normal range, and grid can maintain that normal range, the acceptable range, for at least 5 minutes. After that 5 minutes, the DER should make sure that they are synchronized with the grid. It could be voltage, frequency, it actually should be voltage, frequency, and the phase angle. Okay, then they are allowed to start the reconnection process. Now, the limit for this synchronization, this voltage should not be lower or higher than plus minus 10% of nominal voltage. This means synchronization of the voltage. If the frequency has plus minus 0.1 hertz deviation from the grid frequency, then we could say that we are synchronized regarding the frequency. And if the phase angle difference is less than 10 degree, then we can say, okay, that the phase angle also is synchronized with the grid. Now, we said after those conditions, 5 minutes of healthy grid and the synchronization, now we can start the reconnection, but it should be a ramp rate increase in power, which is a default is 1% per second. Okay, per 1 second. You can adjust these 1% in an interval of 0.5% to 10%. So you can go faster than 10% per second, and you can go slower than 0.5% 45% per second. Okay, this is the discussion that we have for IEEE 1547, which defines the requirement for integration of the distributed energy resources. If you have any question, please let me know. Otherwise, thank you for your attention.